Hello everyone. In this session, we are going to see about a problem on simply supported beams in the unit deflection of beams of strength of materials for mechanical engineers. So the given problem is a beam AB of length 8 meter is simply supported at its ends and carries 2-point loads of 50 kN and 40 kN at a distance of 2 meter and 5 meter respectively from the left support A. Determine deflection under each load, a maximum deflection, and the point at which maximum deflection under each load. Maximum deflection and the position at which maximum deflection occurs. So take E is equal to 2 into 10 power 5 Newton per mm square and I is equal to 8.5 into 10 power 6 mm power 4. So given problem is a simply supported beam, right? So which means at its two ends there will be a support. It can be either roller support or fixed support, whatever, but the beam has support at its both ends, right? That is a simply supported beam. Its length is 8 meter and the point loads are 50 kN and 40 kN at a distance of 2 meter and 5 meter respectively from the support A. So determine the deflection under asking question is deflection under each load. So this point at C point, at D point, the deflection should be found out, and the maximum deflection and the point at which maximum deflection under each load, and also the maximum deflection since the loads are in between the point A and B, hence the maximum deflection will be at this point between C and D. This area will have the maximum deflection, right? And the other data are Young's modulus for this beam is 2 into 10 power 5 Newton per mm square and the inertia will be 8.5 into 10 power 6 mm power 4. So this is the diagram given, right? A, B, simply supported beam. So there will be two supports and 50 kilonewton of point load at a distance of 2 meter from A and 40 kilonewton of point load from the distance 5 meter from the point A, right? So as we know that the assumptions in the beam theory, that is summation of moment is equal to 0 and summation of forces equal to 0. So moment is nothing but load into perpendicular distance, right? So minus 50, since consider the anti-clockwise direction, hence the point loads will be at the negative. So minus 50 into distance 2 meter minus 40 the load and the perpendicular distance is 5 plus RB will become the positive since in anti-clockwise direction it is representing towards the upper side, hence plus RB into at a distance of 8 meter, 3 meter plus 3 meter plus 2 meter, hence it becomes 8 meter is equal to 0, and on solving this we will get RB, that is reaction at the point B will be 37.5 kilonewton, right? And the second assumption, summation of forces equal to 0, that is REA in positive direction minus 50 kilonewton minus 40 kilonewton plus RB, right, which is equal to 0, and substitute RB is equal to 37.5, we can able to find RA is equal to 52.5 kilonewton, hence that is substituted in the diagram itself. And now we have to take a point on this beam, that is in between A and B, hence a line is drawn and the distance will be x, since we have to find the maximum deflection. This point x is taken and hence the moment is equal to this reaction, that is 52.5, a reaction at point A into the distance x modulus of minus 50 will be the point load at a distance x minus 2, right? Since from on considering this only we can able to find the maximum deflection. So minus 50 is a point load into the perpendicular distance is, from this x we have to find the distance, that is x minus 2, and modulus of this point load 40 kilonewton at a distance of x minus 5 kilonewton meter. This will be the moment for this simply supported beam, taken x as a distance, and hence EI d square y by dx square is equal to m, since this is the relation of beam theory, right? So substitute m is equal to this one, that is ei d square y by dx square is equal to, instead of m we are substituting 52.5 x at a distance modulus of minus 50 into x minus 2 is a distance, and modulus of minus 40 into x minus 5 kilonewton meter. On integrating this relation, this becomes ei dy by dx equal to 52.5 x become x square by 2 plus c1. So this will be the separate one, hence constant one, minus 25 into x minus 2 whole square by 2, right? So 50 by 2 will become minus 25, right? That is minus 50 into x minus 2 whole square by 2. So 50 by 2 gets cancelled and minus 25 into x minus 2 whole square will be there. And modulus of minus 40 into x minus 5 whole square by 2, and minus 40 by 2 will become minus 20 into x minus 5 whole square kilonewton meter square. So this will be the slope for the given simply supported beam with the 2 point loads at a distances. So on integrating this EIY, since this is also a double integration method, hence ei dy by dx will become y. This will be the slope, that is deflection. Deflection for the given simply supported beam is equal to 52.5 x cube by 6 plus c1x plus c2. c1 is the constant. On integrating this, c1 will become c1x plus c2 is the second constant, minus 25 into x minus 2 whole square will become x minus 2 whole cube by 3, and minus 20 into x minus 5 whole cube by 3 kilonewton meter cube, right? This will be the deflection. So since this is the diagram for the reference, and at x equal to 0 there will not be any deflection, right? Hence y becomes 0, and so the constant c2 will become 0. At x equal to 8, that is the entire length, there will not be, at point b there will not be any deflection, hence that can be substituted in previous equation, that is in slope, that is eiy equation. So 0 is equal to 52.5, instead of x 8 is substituted, so 8 cube by 6 plus c1 into 8 minus 25 into 8 minus 2 whole cube by 3 minus 20 into 8 minus 5 whole cube by 3. So c1 become minus 335, that is a constant one, value of constant one. So at c, so x equal to 2 meter, right? At this point c the distance is 2 meter, hence x is equal to 2. So on substituting in deflection equation, that is eiy, so since it is a point c, hence y is represented as yc, that is deflection at point c is equal to 52.5 into, instead of x 2 is getting substituted, so 2 cube by 6 minus, instead of c1 minus 335 into 2. Since this on solving this, eiYC is equal to minus 600 kilonewton cube, and ei is equal to 2 into 10 power 5, that is the value of Young's modulus is 2 into 10 power 5, and the value of I is 8.5 into 10 power 6. It is given in the question, right? In the first slide it is given. So ei becomes 1.7 into 10 power 13 Newton per mm square. Hence this can be rewritten as ei is equal to 1.7 into 10 power 4 kilonewton meter square, right? This mm is getting converted into meter, and hence, and also Newton is getting substituted in terms of kilo, and hence this relation becomes ei is equal to 1.7 into 10 power 4. So substitute this ei value in this relation, hence the value of ei is 1.7 to 10 power 4, yc is equal to minus 600, hence yc will become minus 0.0353 meter. Since the value of EA is substituted in terms of meter, hence the deflection will become 0.0353 0.0353 meter. It can be converted into mm. So the deflection at point C, this point, right? YC is equal to 35.3 mm. Since the deflection, the load is applied like this, hence the deflection will be this one, downwards, and hence the arrow mark is shown like this. And at a point D, since we had found out the deflection at point C only, now we have to find the deflection at point D. At D is equal to x, the value will be x will be 5 meter. So substitute x equal to 5 in the deflection equation, that is EIY. So instead of y, it is rewritten as yd, that is deflection at point D is equal to 52.5. Instead of x, we are substituting 5. So 5 cube by 6 minus C1 value minus 335 into x value 5 minus 25 into 5 minus 2 whole cube by 3. And the value of EI is already calculated. So substitute EI value 1.7 into 10 power 4 y suffix d is equal to, on solving this we will get minus 806.25. So yd will become minus 0.04743 meter. Since EI value is substituted in terms of meter, the value of yd is 0.04743 meter. It can be converted into mm, and the deflection is represented as downward arrow. So yd is equal to 47.43 mm yd, that is deflection at point D. So now we have to calculate the maximum deflection. So maximum deflection, consider dy by dx equal to 0. So deflection is likely to be maximum between C and D. Since these are the point loads on a simply supported beam, hence the deflection will be maximum at this area, that is between C and D. From the image we can able to understand this concept, right? So dy by dx equal to 0. Hence on left hand side in slope equation, right, that is ei d square y by dx square, that equation in the previous slide. So left hand side will become 0. 52.5 into x square by 2 is equal minus c1 value minus 335 minus 25 into x minus 2 whole square. So this relation can be rewritten as 1.25 x square plus 100x minus 435 equal to 0. Hence the value of x becomes in terms of two values. So that value has been found out from this equation, x equal to 4.136 and the other is a negative one. Hence the positive ones is taken and substitute x equal to 4.136 in the slope equation, that is ei y max equal to 52.5 into, instead of x 4.136 is substituted, whole cube by 6 minus c1 value into x minus 25 into x value is 4.136 minus 2 whole cube by 3. So the value of ei is 1.7 into 10 power 4. Hence the value of y max will become minus 0.04986 meter. So y max is equal to 49.86 mm, right? In terms of mm, the maximum deflection is converted. So deflection is represented in downward arrow mark. So in the previous slide, that is the deflection is maximum deflection will be maximum at the point between C and D. That image in the previous slide we can able to clearly understand this concept. Hence the y max, the maximum deflection becomes 49.86 mm. Thank you.